Consider two sinusoidal waves with the same frequency, wavelength, and amplitude traveling in opposite directions. Two waves are moving on a string, and eventually these waves are going to meet with each other and interact with each other. This interaction is going to cause a superposition, and so the superposition at certain point in time will be different. So let's take a look at the snapshot graphs of at different moments in time during the period of a cycle. Let's take a look at the first one on the top, where the blue wave is going to the right and the pink one is coming to the left. So when they superimpose, we end up having this green wave that I'm going to highlight now for you. So this green wave with a certain amplitude. The next snapshot, the crests of the waves are coming closer to each other. So the wave, created new wave, will be a little bit higher in an amplitude. So sometime later, the amplitude is gonna increase even more. Okay. So at the quarter of the period, you can see the crests overlapped. When they overlap, you get the maximum of the amplitude of the wave. So you can continue looking at the snapshots. You will see when the waves are splitting apart again, the blue is still going to the right, the amplitude is decreasing of our new superposed wave, and it is going to decrease even more and decrease even more until when the crest of one wave and the trough of another wave meet each other. Well, here's the crest of one wave and the trough of another wave. When they meet each other, what happens? The wave cancels out. So this is completely canceled out. So you can repeat this until at certain point you will come to the original time equals 0 state. Now, if we collapse these graphs into a single graphical representation of a standing wave, we will get a wave looking like this. A striking feature of a standing wave pattern is the existence of some points that never move, and those points are called nodes. So as you can see, these points right here, they never move. They always remain at the same place. So those are nodes right here. So node. Halfway between the nodes, there are points where the particles in the medium oscillate with the maximum amplitude. So, and those are these points right here. So, right here between the nodes. Okay, so those are called antinodes. The nodes are spaced half a wavelength away from each other. So if this is half a lambda, this would be lambda, this would be 3/2 lambda. And similarly, you can see that antinodes are also half a wavelength away from each other. So this one is also 1/2 lambda. Now let's discuss the mathematics of the standing wave. A sinusoidal wave that travels to the right along the x-axis with the angular frequency of omega that equals 2 pi f and wave number k equals 2 pi over lambda I'm gonna denote this as y to the right would be represented as a sine kx minus omega t, where this minus means that the wave is going to the right. Similarly, with the same angular frequency in a wave number, wave that is going to the left will be written as a sine kx plus omega t. Now, according to the principle of superposition, the net wave or the net displacement of the medium when both waves are present is the sum of these two waves. So I can write yxt equals yr plus y that left, that equals a sine kx minus omega t plus a sine kx plus omega t. We can simplify this expression by using trigonometric identities. Let's recall this. Sine alpha plus minus beta equals sine alpha cosine beta plus minus cosine alpha sine beta. So this is something that we're going to use to simplify our expression. Then we will end up having yxt equals a sine kx cosine omega t. Let me put this in parentheses like that. Minus cosine kx sine omega t, and then plus, I'm going to write a little bit on the bottom, a sine kx cosine omega t plus cosine kx sine omega t. This leads us yxt equals 2a sine kx cosine omega t. So if you take a look at this expression, we can say that this part that I highlighted with pink, it's the amplitude, because we know the form of wave function. So I can say that I can call ax equals 2a sine kx. And this is called amplitude function. Now I can rewrite my wave equation yxt equals ax cosine omega t. This amplitude reaches the maximum value. A max happens when it is 2a and sine kx equals 1. And our displacement yxt is, you can see it's neither a function of x plus vt, nor it's a function of x minus vt, which means this is not a traveling wave. not a traveling wave. Instead, this cosine omega t term describes a medium in which each point oscillates in a simple harmonic motion with the frequency of omega over 2 pi. The function, the amplitude function ax equals 2a sine kx gives the amplitude of oscillation for a particle at any position of x. So if we take a look back to our standing wave, we will see at the nodes the amplitude is actually 0. To find the positions of these amplitudes, we just have to require that the amplitude function should be 0. So let's go ahead and require this amplitude function ax to be 0. So we'll say a of x that equals 2a sine kx equals 0. The sine function is 0. This is only can happen when sine kx equals 0. Let's put parentheses in here not to get confused. And sine function is 0 when at the angles of multiple of pi, integer multiple of pi. So in other words, I can say these angles kx at certain, I'm going to put the m here like a subscript because there are many of these values, would be equal 2 pi I meant m pi, not 2 pi, where m equals 0, 1, 2, 3, and so on. From the other hand, we know that the k equals 2 pi over lambda. So xm equals m times pi. Now I can find out where the each x is. So the pi's will cancel out. We'll end up having xm equals m times lambda over 2. So it's the same thing that our picture right here shows, where we have 1/2 lambda, 2/2 lambdas, 1/2 lambda, 2/2 lambdas, 3/2 lambdas, and so on. That's what we got mathematically in here. So of course m is going from 0 to 1 to 0, 1, 2, 3, and so on.